Hi guys, so this is problem 49 from chapter 8, and this section is about the step response of an RLC, series connected RLC circuit. So in this problem we have a 50 volt independent voltage source connected in series with an 8K resistor, a 160 millihenry inductor, and a 10 nanofarad capacitor. And the problem, so what happens is that at time 0, this voltage source suddenly becomes 250 instead of 50. And we're looking for the equation that describes what's happening with the voltage across the capacitor. So that is what happens. So I'll represent that by saying at t equals 0, this will go to 250 volts. Okay, so the first thing you always want to do is you always want to find out what kind of response we're looking at, because the type of response drives the general equation. So we always, step number 1, no matter what you're doing, series, parallel, whatever, you always have to find the type of response that's going to be driving your equation. So that means you need to find alpha and omega naught. So let's go ahead and do that. Alpha is going to be, for a series connected circuit, alpha is R over 2L. So that's going to be 8K over 2 times 160 millihenries. And when you do that math, you will come up with alpha is 25,000. We're going to park that value here because we need it later. So 25,000 is alpha. Now, omega naught is equal to the square root of 1 over LC. So that's going to be the square root of 1 over, I'm going to change pens, this one is not very good. So the square root of 1 over 160 millihenries times 9 nanofarads. Okay, do that math and you should find out that omega naught is 25,000 also. So we have a case where alpha is equal to omega naught, so that means we have a critically damped response. Critical. So we have a critically damped response circuit. So that narrows down our equations by quite a bit. So now we know what equations the response will take the format of. So at the end of chapter 8, there's a summary where they tell you what the general equations are, along with the coefficient equations. So for a critically damped circuit, we have these equations. We got V of t, well, they say x of t. X of t is equal to x final plus, shoot, I never have enough room. Okay, so we have, at the end of the chapter they put an x of t. The x is going to be whatever it is that you're looking for. In this case, we're looking for v. So our general equation will take the form Vc of t, the general capacitor equation. Voltage across the capacitor is going to be V final, the final voltage across the capacitor, plus d1 t e to the minus alpha t, plus d2 prime e to the minus alpha t. Alright, so we already know one piece of that. We already know this, the alpha is going to be negative 25,000. We solved that already. So negative 25,000 t, negative 25,000 t. And what else do we all know? We know that the initial voltage across the capacitor is 50. We know that the final voltage is 250 because in a series connected circuit, after a long time, it's going to charge up to, it becomes an open, the capacitor becomes an open after a long time, and as an open, it's going to take the voltage drop of the voltage source, and that's going to be 250. So we already have a whole chunk of our equation. So VC of T is equal to 250. That's the final voltage. Now, all that's left is finding D1 and D2. And for that, we're going to use we will be using the coefficient equations. So, in the coefficient equation, it says x of 0 is equal to xf plus d2. The x is whatever thing that you're looking for, in this case, voltage. So that's telling me voltage across the capacitor at time 0 is equal to voltage final across the capacitor, final voltage across the capacitor, and plus some d2. Well, I know that what my voltage is across the capacitor, that is 50. That's my initial voltage. I know my final voltage is 250 plus D2. Therefore, D2 must be negative 200. Okay? So now I found D2. That's going to be negative 200. Negative 200 e to the negative 25,000 t. Okay, now all that's left is to find D1. And for D1, we have the coefficient equation that says some x of 0. X of 0 is equal, dx dt of 0 is equal to D1 prime minus alpha D2. That is how we're going to find our D1 prime. So the x is whatever we're looking for, in this case capacitor. So it's going to be dVc 0 dt is equal to D1 prime minus alpha is 25,000, so 25,000. D2 is negative 200, negative 200. All right, so negative 25,000 times negative 200 is 5 million. I'm going to replace that with 5 million plus 5 million. I almost have it. I need to find out what is the VC of 0 dt. That term is asking for the rate of change of voltage across the capacitor at time 0. So it's not going to immediately charge, because one of the properties, a key property of the capacitor, is that it cannot change voltage instantly. It can change current instantly, but not voltage. Therefore, since this is asking for a rate of change of voltage, the answer is 0. Whatever, it was 50 before time 0, and it'll be 50 right after time 0. It's the same. So this is 0. So therefore, D1 prime is going to be negative 5 million. So negative 5 million. Okay, so let's take a look. If we're taking a test, we want to make sure at least this equation makes sense for time 0. So at time 0, we have 0 here, so this term goes away. And then e to the 0 power is just 1, so we have 250 minus 200, 50 volts, which is what we have at time 0. And then at time infinity, after a long time, at time infinity, I have infinity times 0, because e to infinity power is e to the negative infinity is 0. So this goes away because actually time infinity, this is undefined. So I have something, no. The time infinity, this tapers off to 0. That's right, because this e to the infinity power drives the whole thing. So this tapers off to 0, and we could actually prove that with L'Hopital's rule, because infinity times e to the infinity is actually undefined. So, but we could prove that with L'Hopital's rule, which I'm not going to do. But this goes to 0, and this term, e to the minus infinity, goes to 0. So over a long time, this will approach 250. So this equation looks pretty good for initial conditions and also for final conditions, and it's actually the answer. So, Answer this problem. V, the voltage drop across the capacitor for this particular circuit can be described with VC of t is equal to 250 minus 5 million t e to the minus 25,000 t minus 200 e to the minus 25,000 t. I hope that helps. Oh, please share this video because I need more people to find this channel so it'll be more interactive, and that's just a function of numbers. So if you got help, please share the video. Thank you.